So inference. We're going to take a look at inference for samples and observational studies, and a little bit of inference for experiments, etc. All right, so please write some of this down with me. It'll help you stay awake. It'll help you keep going, but I will, like always, push these notes out to you via OneNote so you can have them in their entirety. If you don't see them, remind me and I'll push them out. It means I just forgot. All right, let's do this. So we're going to start with inference for samples. Okay, inference for samples. So you have an observational study, and when that observational study, you get the results, you do your summary statistics, and if you took a random sample of a population, you can make conclusions about that population. Now, you can't say something is causing something else, all right? A correlation or an association does not imply a causal relationship, but you can make some assumptions and some inferences about a population based off of a sample, okay? Now, you just have to make sure that you only make those inferences about the population that you took your sample from. So if I sampled Edison High School students about who do you want to be president, I couldn't take those results and infer something about all of Fresno. All right, well, I can't say, oh, Fresno prefers this candidate because my sample from Edison High School says this. I can't do that. But I can infer something about Edison High School students that way. All right, so as long as my conclusion only is referencing the population I took the sample from, I'm good. Okay? Now, that doesn't mean if I do that, that my sample and my population are exactly the same. So this is a really important idea, this idea of sample variability. Random samples of the same size from the same population will produce slightly different estimates. All right? In an easier way of saying it, samples are always going to be different from one another. And if the samples are different from one another, well, they got to be different than the population by a little bit. We saw this at work with our crop example that we did. Remember the river going next to the crops? All right, so I got a few more data points. Then I got lazy and stopped tracking them because I had enough. At least I thought I had enough. So here is the simple random sample of the corn crop problem. And as you can see, we had many different results. Not every sample is the same. You were randomly generating numbers. So hopefully that gets you the idea that, hey, sample variability is a thing. Not every sample is going to be the same. All right? So this has a special name. All right? When I have a dot plot or a scatter plot or, well, not a dot plot or some sort of distribution of a bunch of samples, we have a special name for it. This is called a sampling distribution. All right, and when you say it, you have to say it like this, a sampling. All right, you got to have an emphasis on the ling just to be obnoxious. I'm always going to do it. You're always going to do it. It's how it's going to happen. It's a sampling distribution. And so what that means is each dot, all right, if I pick this dot, what the heck does that dot mean? That's not an individual person or an individual crop or anything. That is a group. That right there is the average of an entire sample. In this case, of 10 crops. Okay? Because again, I took your data. You all clicked enter on your calculator 10 times, and then you found those 10 crop sections and you averaged them out, and then you gave me your average. So each of these dots is one of your works, one of your samples of 10 crop sections. And that's kind of weird when each dot is not individual. Each dot is not one thing. Each dot represents the average of an entire sample. That's a sampling distribution. Now, usually you don't get to do this over and over again. Usually you get one sample. And so you don't know if you got this dot over here towards the right or if you got this dot over here towards the left. Okay? Because you usually don't do this over and over again. And so oftentimes this is a hypothetical thing, this sampling distribution, because we ain't got time to take 100 samples. We only have time to take one sample. Which is why our different sampling methods can be very important, because they reduce this variability. And so I think I showed third period a bit of this. Here is what that same idea looks like. 42 samples. Each sample is 10 plots of land for the vertical stratified random sample. Here you can see there is much less variability. Almost all our samples were within that small little range right there. Much less variability, which is why stratified random samples are great. They reduce the variability. They're more accurate, you could say. All right, whereas the SRS was much more spread out. Now, a stratified random sample won't do anything for you if you don't pick your strata correctly. So here is the horizontal strata for that crop problem. As you can see, it is still very, very spread out. So if you don't pick your strata correctly, it don't do nothing for you. Okay? You have to pick them correctly. You have to have some sort of commonality that affects what you're looking at for a stratified random sample to do something. But it's a great illustration for how stratifying can really give you better results. But in all of these are sampling distributions. Each dot, all right, represents the average of an entire sample. All right, not just one individual, but an entire sample. I can't say that enough. It's going to become more and more of an important idea and a complicated idea. Each dot is actually the average of an entire sample in that case. All right, a little bit more about sampling. All right, if you want, one way to get a more accurate sample is to use like a stratified random sample. That's great. Another way is simply just to use a larger sample size. And hopefully that makes sense. Asking 50 people is a whole lot better than asking 10 people. Because who knows, maybe you got 10 weirdos. All right? Or of those 10, like 2 of them were weirdos. 2 out of 10 is a pretty big percentage, right? But if I had 50 people or even 100 people in my sample, the chances that the weirdos, I mean that in the nicest sense of the word, by the way, the chance of getting enough weirdos to influence your results is much less. Okay? So larger sample sizes will tend to have estimates closer to the population. Okay? Larger samples are good. Smaller samples, not so much. All right, that's the general idea there. All right, let's put a few things together here. Here's a good example from the book that takes some of this into account. How much do NFL players weigh on average? In a random sample of 50 NFL players, the average weight is 244.4 pounds. So, do you think that 244.4 pounds is the true average weight of all NFL players? Explain your answer. So here, hopefully, we can see that no, we don't actually believe the real average weight of all NFL players is exactly 244.4. All right, because every sample will be a bit different. We only have one sample here. So we don't know, hey, did we get this dot right here way on the low end? Or maybe did we get this dot way over here? Or maybe we got one right in the middle. We only did one sample. We don't know for sure. Okay? And so we know that this 244.4, it's probably going to be close. But we definitely know it can't be exact. Okay? So the true average weight of NFL players is not 244.4 pounds. Because of sample variability. Now, we're hopeful that it's close. A sample of 50 is pretty big. We're hopeful that it's going to be close, but we know it's not going to be exact. All right. Part B, which would be more likely to give an estimate close to the true average weight of all NFL players? A random sample of 50 or a random sample of 100? All right, so hopefully there we know, hey, more in your sample is better. So the 100 players would be better for a sample because we know larger samples will be closer to the actual proportion. All right. Larger samples will give proportions closer to the population. So a sample of 100 would give us a closer estimate. I'm hoping that makes some sense. It's fairly self-explanatory, maybe. All right. Couple concepts there. Now, usually when you take a sample, or a research association takes a sample, and they give this sample to the public and say, hey, here is our research, and our inference, but here's our research. Usually, if they're reputable, they will give a margin of error along with their estimate, okay? They won't just say, hey, the average weight of a football player is 244.4 pounds. We know that's not the case. All right? We know there's sample variability. It cannot be exactly, almost 100% cannot be exactly 244.4. Maybe we got lucky, but probably not. Okay? So you can calculate a margin of error. How good is your calculation possibly? Now, we don't know how to calculate this yet, but I hope we can understand what it is. Second semester, we will calculate margin of errors. It's a big, big part, okay? But you can understand what they are right now. So the sample of 50 NFL players above gives us an average weight of 244.4 pounds with a margin of error of plus or minus 14.2 pounds. Hopefully you have seen this in like political polls. Sometimes they'll say, hey, this candidate is ahead by, a 50 to 48 margin with a margin of error or plus or minus 2%. Okay? Hopefully, if they're reputable, they give you some sort of margin of error. We know the actual average is not 244. but we're pretty sure it's somewhere between 244.4 plus 14 or minus 14. So the true average, we think, is between, so I take the 244 and I add 14.2 and I subtract that. So I'm going to do that real quick on my cat. 244.4 minus 14.2. So on the low end, we think it could be as low as 230. And on the high end, 244.4 plus 14.2, 258.6. The true average, we think, is between 230 pounds and 258 pounds. All right, that's what our margin of error tells us. A reputable research firm will definitely give you the margin of error for their sample results. A less reputable one will definitely leave that out because sometimes this number can get pretty big and then your numbers mean much, much less. Okay? But we don't know how to calculate that right now. So for now, it has to be given to you. Second semester, though, we will calculate margins of errors. It's a big, big part of what we do. All right, so I'm going to stop talking here for a few minutes. If you didn't see the Nearpod link in the general channel, I've got a few questions about this so you can try a few things like this out. The first 5 slides of the Nearpod. It's 2 questions, essentially, 2 scenarios, and then a few questions for you. See if you can put some words to paper, or words to screen, I guess. Yeah, words to screen. Open that up. It's self-paced, so you can go at your own pace, but only do the first 5. All right, let's talk about these here, ladies and gentlemen. The first one looked pretty good. I don't want to go over that one, but the being born on the weekend versus the weekday, let's talk about that, all right? So first one asks, so are you more likely to be born on the weekday or the weekend? Now that doctors can oftentimes choose when you will have a cesarean section, all right, a C-section. Also, they didn't say this, but inducing labor could also be a thing. Man, when my wife had our son, our second kid, yeah, we like signed up for a time, and it was like going on vacation. We packed our suitcase, we loaded the car, we dropped off kid number 1 with the grandparents. We're like, all right, we're going to the hospital now. It's like it was planned and everything. She didn't have a C-section, but they induced. So what does this mean right here? That dot right at 40. So that represents, all right, that represents, in this case, it was a simulated sample. It wasn't an actual sample. A simulated sample where 40 out of, I think they were doing samples of 73, where 40 out of 73 people, I mean, it's a simulated sample, so I might put air quotes over people. 40 out of 73 people were born on the weekend. All right. That's what that number means. There was a sample where 40 people were born on the weekend in a sample of 73 people. All right. Can I see what the rest of the question was? I can't. So then I asked, So is it weird that this doctor sample, the doctor, when they did a sample of real people, they got 24 born on the weekend? Is that so crazy unusual? Or could it happen just because of sample variability? Well, we come over here and take a look. How many were born at 24 or less? All right, because we think 24 is unusually low. But is it? Well, if we take a look at that, how many dots are there? 1, 2, 3, 4, 5, 6. So 6 samples in our simulation, just by chance. 6 out of 100 simulated samples were 24 or less. So that would translate to a 6. There's a 6% chance. All right. So 6% of samples would be 24 or less. Now here you got to think, all right, is that so crazy unusual that we think this doctor's results were just by chance? Oh, you just got unlucky. That's why you got a number that low. All right. Getting 24 is perfectly reasonable. Or getting 24 is so crazy, there must be something happening here. You wouldn't get 24 if it was just randomized or sample variability. So here we got to make a judgment. Is 6%? I would say that's not impossible. With a 6, there's a 6% chance essentially that that doctor's sample is low just because of sample variability. All right, so 6% of samples in the simulation were 24 or lower. So the doctor's results, I might even say the doctor's low results, could just have been sample variability. All right. Even if, we're assuming that there is no difference in being born on a weekend versus weekday. And if that's the case, if you randomly select 73 people, it's very possible that only 24 of them will be born on the weekend. All right. 24 or even fewer. So how crazy. If the doctor had gotten like 20, all right, that's a big if. But if the doctor had gotten 20, it's like, whoa, I don't think that could happen by pure chance. Someone's doing donuts out in my cul-de-sac right now. I can just hear them. That's very distracting. If the doctor had instead, in their survey, or gotten 20 people born on the weekend, well, that never happened by chance. That's super low. And so we think that might not be because of sample variability. That would be because there's actually a difference between the number of people being born on the weekend versus born on the weekday. But 6% is decently big enough. I wish they were giving out donuts, man. I'd be gone right now. All right. I mean, you guys are important and everything. I'm not gonna lie, but I'd be gone. Unless they were Krispy Kreme. Not a fan. All right. We can do this same idea with experiments. Okay. Is something too unusual to be explained by chance alone? So the same idea can be done with experiments. And we call that statistically significant results. All right. When the results of an experiment are too unusual to be explained by chance alone. All right. Kind of like sample variability, but there's no samples in an experiment. All right. There's no samples in an experiment. So we can't use sample variability. But there is still an element of chance in an experiment, all right? Is what you're seeing the treatment at work, or is it just general variability with all the variables that you couldn't control? Okay, people are different. So we're going to go back to our Coca-Cola experiment. Does caffeine raise your heart rate? So we got some hypothetical numbers. So here's the data from a class that did this experiment. Okay, so they had 10 people take the caffeine, 10 people take the soda with no caffeine, and there are their results. Now, the way they got these dot plots is they calculated the change in the pulse rate. All right, so how much did your pulse go up? If it's negative, your pulse went down. It helps combine our data a little bit. So we have all these numbers, and they found that on average, the people that drank the soda with the caffeine increased by 3.2 beats per minute. And those people without the caffeine, they actually also increased, but only by 2. All right, so let's summarize that here. The students who drank the soda with caffeine had an average increase of 3.2 beats per minute, while the students who drank the soda with no caffeine had an increase of only 2 beats per minute. So there is a difference of 1.2 beats per minute between the two groups. So now we got to decide, is that difference big enough to assume that our treatment did something? Did the caffeine actually do something? Because it kind of looks like, yeah, the caffeine, they had a higher increase in heart rate. But is that increase enough to say, hey, our treatment did something? Or was it just the fact that, people are different, and when we randomly assigned people, we just happened to get people into the caffeine group who were going to have higher heart rates anyways? All right, were we just kind of unlucky in our random assignment? We have to make that decision. And you don't just be like, oh, well, I think, no. You got to have a reason. All right, there's a way we figure this out. So one way we can do is another simulation, kind of like the simulation in our previous problem. Oops, I want to keep that, I wanted to underline. All right, so what we're going to do is we're going to pretend that there is no difference between caffeine and no caffeine sodas. I'll even cross that out. We're going to pretend there's no difference. So we're going to take all of these results. We're going to pretend there's no difference between them, that the variability is just people being different, and we're going to take all of those and randomly assign them to two groups over and over again. Okay? We're going to randomly assign them to groups over and over again to get a distribution of many different trials. Okay? And see what that distribution looks like. So here's what that could look like. It's a simulated difference. So if I randomly put these students into groups of 10 with their numbers that they got. All right, so here, if I take, let's pick, turn off your phone, Bolt. So what does, say, this one dot at the 3 represent? That represents a hypothetical experiment, all right, choosing groups from these numbers. All right, so I would randomly pick 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be my first group. Take their average, take the other group's average, subtract them, and one of those times the difference was 3 beats per minute. One group was 3 beats per minute higher than the other. In a random simulation. Just by pure chance, it got up to 3 beats per minute as a difference. So, do we think it's caffeine or just people being different? Well, our difference was 1.2. So how many of these random trials were 1.2 or bigger? 19 of them. All right, there's 19 trials of these random trials where just regular variability. It's really hard not to say the word sample. It's not a sample. Not a sample. Where just regular variability caused a difference of 1.2 or even more. That's almost 20%. All right? In almost 20% of random assignments, we get a difference in heart rate of 1.2 or more. So it seems the difference in our experiment I need more space. There it is. Of 1.2 beats per minute is not statistically significant. Significant. Yep, I spelled it right. Which means it probably just happened by chance. This probably happened by chance. Because when we ran a simulation of just by chance, this happened a lot. It's not so unusual that it couldn't have happened just by random assignment. We happen to get people who are going to be nervous in this group more than we happen to get in that group. If you remember before, when we did the random assignment, you hopefully create 2 even groups. Are you guaranteed to create 2 even groups with random assignment? No, you hope you do. But every group is always going to be a little bit different. It's going to have some variability in it. How much variability? Well, that's what you run the simulation for. And then you take a look at, all right, here's the variability in simulation. Did my experiment land inside that variability? 1.2 is about right there, right? And if it is inside that variability, then your results aren't statistically significant. Now, if we had an increase in heart rate of like 4, or even 3, I would suppose, even 3 or 4, well, 3 is highly unlikely to happen by chance. That's a 1% chance of that happening. So even if it was a 3, that would still be pretty statistically significant because that probably wouldn't have happened just by chance. A 4 definitely wouldn't have happened by chance because it never happened in our simulation. But the 1.2, that happened a lot just by chance. So therefore, it's not statistically significant. It could probably just have happened by chance. All right. So the random assignment, while it's the best we can do, sometimes, well, it's always going to have variability. And so you don't know, you have to figure out, if your results are statistically significant or not. All right. I don't know if we quite have time for questions 6 through 8, do we? It is 11:13. Maybe we'll do those during our review session next time on the Thursday, eh? That'd be kind of nice to finish those up. I think the Nearpod link is good for 30 days. So we got 30 days to try that out. Your homework. All right, you're reading page 303 to 307. It's a continuation of what we just talked about right now. Take a few notes, write a few things down of the important concepts, and a few problems from the homework there, ladies and gentlemen. All right? Have a good one. Get some rest. Do some makeup work. Hopefully your homework isn't quite as long these last couple of days. See you all Thursday. Oh, it's only Tuesday. How is it only Tuesday? Bye, everybody. Have a good one. Go get some donuts. I want some donuts. I gotta stop recording.